Okay, so in this video, we're going to discuss something called the center of mass. Um, I'm sure I've kind of misspoken and used the word already this semester without defining it. And I don't like to use words before I define them, but this concept is so intuitive that sometimes it just slips out even without me planning. Center of mass is what it kind of sounds like. It's you look at a shape, you kind of think, all right, well, yeah, it's kind of spread out and got arms and legs and whatever, but um, you know, the center of mass is somewhere in the middle. That's basically the idea. Um, More precisely, center of mass is going to be the average position of a chunk of mass, and you're going to weight the average according to mass. So what does that mean? Well, so so it's a weighted average. So let's kind of go through an example like that. Okay, so if you were going to say what's the average position of these, say in the x direction, you'd say, oh well, you'd say you've got 5 over here and 1 over there, and the average position would be pretty close to the 5. Okay, that would give you the center of geometry, the average geometric position. What we're after is the center of mass, because what I didn't tell you is these are all made of styrofoam and that one's made of gold. And so, well, if you know that, that completely changes the story, because basically when finding the typical or average position of a chunk of mass, well, you would need to weight the gold much more when you take the average. So if you're not familiar with the concept of a weighted average, well, it's kind of hard. Usually in class, I have people kind of work out the average position in the X and Y direction of people in the classroom. And I guess I can do that too. You can just imagine everybody spread around the world here, I suppose now. And that would be a really hard thing to calculate, but you can imagine doing it. And there's some place where they're centered. But on the other hand, if I ask you to consider and to calculate the center of awesomeness, clearly it's located right here in the upstairs in my house, because you have to weight the relative awesomeness of different people, and so clearly it's right here. All right, so you get the idea that when the different bits are all the same, then you can just take this normal average. But really, you should allow for the fact that they aren't the same. So you have to include that and somehow count the heavier things more. So it's going to be a weighted average of positions, and you're weighting the average according to the mass. Okay, the formula for center of mass, and we'll talk about center mass in the x direction here. So if I've got the x direction, say that's at 0, we'll say this is at -1, -2, 1, 2 meters. And what we're going to do is what we're after is something like, let's say I've got a particle here and a particle here. I've got 2 particles here and I've got 1 over here. And let's say each little particle has a mass of 10 grams. All right. So if we want to define the center of mass and we want a weighted average of masses or of positions, the formula for the center of mass in the x direction, x center of mass, is the following. For each mass, you take the sum of the mass for each one times the position of each one, and then you divide by the total mass. Okay. Well, okay, let's see how that works. So let's look at this distribution, and we're going to apply this formula. As I look at this distribution, I look at it and I say, if they all have the identical masses, then I can really say, well, most of it's over here, so probably the average position's, I don't know, somewhere around here. I don't know where it is. Somewhere, let's say right there, be my guess. Somewhere between 0 and -1. I'm just guessing. Let's see what we find. So when I use this formula, this tells me to sum over all particles, and for each one, I write down the mass times the position for each one, add those all up, and divide by the total mass. The total mass is going to be 4 times 10, it's going to be 40 grams. So this is going to give me, in the numerator, I get 10 times -2 plus 10 times -1 plus 10 times -1, or I could have said 2 times 10 times -1, plus 10 times +2, because this one's all the way over here on the right, where things are positive, divided by the total mass, which was 40 grams. Okay. Well, I should have been more careful here. I should have put meters, 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 meters. And I should have put grams, 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 grams. Notice the grams are canceling, and everything else comes out with the meters. So it comes out with units of length. That's fine. It all works out. And if I add these all up, I get negative. So I get -2, -4, +2. I get -2 times 10. I get -20 gram meters upstairs. So the answer here is going to be -20 gram meters divided by 40 grams equals 0.5 meters, and it's negative. So it's right there, kind of where I eyeballed it. You know, humans are really good pattern recognition machines. We have good intuition. We're good at looking at things and kind of guesstimating with our gut, things like that. Sometimes things lead us astray, but we're pretty good at that. -0.5. Okay, so it's an average position, and it's a weighted average. You're weighting things according to mass. What about things spread out over 2 dimensions? Well, you just do the same thing twice. You can compute the x center of mass. That's just going to be, so you don't worry about y, only look at the side-to-side positions. Divided by the total mass. And then you can also turn around and define the center of mass in the y direction. And then you're going to include y value positions and ignore x. So that's really easy. I won't do another example because it's really no different than what we just did. If we were in class, I'd have you guys calculate the center of mass for people sitting in the classroom, but that's okay. Okay. Center mass, x, center mass, y. Sorry, I lost my train of thought. Sorry, it's getting late. All right, so that's how you define the center of mass for point particles. Oh, yeah. Okay, right. Now, what about, that's how you do it for point particles. What about a continuous blob of stuff? Well, let's go back to our formula. Let's say we wanted to find the x value of center of mass. We said that that was equal to the sum of the x value for each piece times the mass of each piece, and you divide by the m total. We're going to do the exact same thing. We're going to take this object, we're going to break it up into little cubes now, and each one's going to have a tiny volume. And we're just going to turn this sum into an integral. So it would become, for this 3D shape here, it'd become an integral over x times the density dV divided by the total mass. Okay, so the sum becomes an integral, and the mass of each little cube is given by rho dV. And that's how that would go. Piece of cake. The integrals could be kind of gross depending upon the problem. But for most things that we do, we will usually have shapes which are symmetric, like spheres, rings, squares, things like that, where the mass is evenly distributed over them. And then if the density is constant, well, it pretty much always turns out then that the center of mass will be in the middle. In the center of symmetric when I say center, I mean the geometric center of symmetric shapes. And so for something like a sphere or a square or, I don't know, equilateral triangle, you don't have to do any calculus. You just look at it and you just say, center of masses are going to be right in the middle. For irregular shapes, you really do have to do the calculus, and it can be kind of complicated. We won't have 3D examples, but we could do a 1D example. So let's do a one-dimensional example of center of mass, where the density is not constant. So let's imagine, well, let's go back. We had a previous example where we had a one-dimensional shape at length 1 meter, and we had a density that grew linearly, and we said that lambda equaled 10 grams per centimeter squared times x, where x was in centimeters. If I want to convert it, maybe we'll just do it in centimeters. Yeah. Okay, so this is the same example we had earlier. Lambda is not constant, it changes with x. So that means you can't just say that the total mass is lambda times 100 centimeters. You have to do the calculus. Thankfully, we did the calculus for this already, and we found that the mass equal, the total mass, this was in the last video, equals, oh shoot, I believe it was 100 kilograms. Yeah, because it'd be 10 times 100 times 100. So that would come out as 100,000 grams. Yep. Okay. So that's the total mass. Now let's calculate the center of mass position. Where is the average position of, if you were to kind of randomly reach in and pull out 1 gram, or kind of reach in, pull out 1 gram, put it back, pull out 1 gram, put it back, do it a whole bunch of times. On average, where would your hand be? Well, most of the mass is over here, so you would expect on average something over here. So I'm going to guess that the answer is somewhere like 75, but I don't know. We'll do the math and we'll find out. Okay? 75 centimeters, that is. So I did the last examples, and this example I'm doing with centimeters, but you could do it with meters too. And on sapling, that's probably what you should do. Okay, so to find x center of mass, that's going to be the integral of x times lambda, which itself is a function of x, times ds, but that's going to be dx because it lies along the x-axis, from 0 to 100. And I have to divide by in total, which is 100 kilograms. So that's going to be, the numerator is going to be 10 times an integral from 0 to 100, and I have an x from here, and I have an x from here, so I get x squared dx over 100. And then I'm going to get 10 over 100 from this stuff times x to the third over 3 evaluated from 0 to 100. So that's going to be 1 over 10 times times 1,000,000. No, 10 to the 6. Centimeters. I should be careful here. My units are getting, this is 100 kilograms, but this is 10 grams. So this is actually 100,000. There you go, 100,000. Which makes this 1 over 10,000. There we go. Whew. Divided by 3. So what do I get? Okay, so I get 1,000,000 divided by 10,000. So that's going to cancel 4 zeros. And I get 100 over 3. So actually, my guess was wrong. It comes out to be 100 centimeters over 3, so it's going to be like 33. That doesn't seem right. That doesn't seem right. So let's fix that. I must have a mistake. What did I do wrong? It seems to be what I get. I tell you what, I will think about that and make sure I didn't screw it up. But that's what I seem to get. That doesn't seem right though, because most of the mass is concentrated here for larger position. The average position should have been closer to the far end. I must have got things backwards somehow. So I will work that out and post a correction in my next video.